we're going to introduce some of the key terms and types of formulas we're going to be using during our organic chemistry study. So let's just have a think about what is organic chemistry. Organic chemistry is the study of the chemistry of carbon-based compounds, but there are just a few exceptions. So we're looking at the chemistry of things containing carbon. Can you think of anything that is carbon containing that would be classed as inorganic? So we're looking at carbon-based compounds that accept things like carbon monoxide, carbon dioxide, metal carbonates like sodium carbonate. These are non-organic ones, and things like diamond and graphite as well. What sort of bonds do we get when we're bonding carbons? Have a think, what sort of bonds would carbon form in its organic compounds? So it's forming bonds to other carbons and to hydrogens, maybe to oxygen, maybe to bromine. What sort of bonds does carbon form? So we should know it forms covalent bonds. Do you know how many and what shape you get around carbon quite often? So how many bonds does carbon form? Carbon is in group 4. How many bonds would it need to form to get electron configuration of a noble gas? So each C atom forms, to get from group 4 to a noble gas configuration of P6, you need to form 4 bonds. That gives you 8 in your shell. So 4 covalent bonds. Every carbon always forms 4 covalent bonds. What we're going to do is look at all the different ways that chemists are going to represent organic compounds. And to do that, we're going to take a particular compound. So I'm just going to draw out the compound butane. This is a diagram of butane. You might have come across butane at school. And we're going to look at some different types of formula. So the first formula, we're going to look at something called the molecular formula. That tells us simply how many of each atom that are in that compound. So the actual number of atoms of each element. And we usually write that in the form C and then how many C's. So how many C's are there? And then H and how many H's. So butane would be C4, and if you count up those H's, H10. This would be its molecular formula. If we go back here, we can write that in. So there we go, butane is C4H10. The next type of formula has this definition, and we have covered this before, so see if you can remember which is the simplest whole number ratio of atoms of each element present. So that's the empirical formula. So what would be the empirical formula of butane? So have a think, what would be the empirical formula of butane? So the simplest ratio of 4 to 10 divisible by 2, C2H5. If I had found the empirical formula from calculations and I needed to find the molecular, what other bit of information would you need to know? So we could add up this empirical formula and see that we had 2 C's at 12, that's 24, and 5 H's at 1 each, so that gives us 29. How would I know that I needed to make it be C4H10? And to do that, I would need to know the MR. Okay, so we've got our molecular formula, the actual number, and our empirical formula, the simplest whole number ratio. Our next formula is called the structural formula, and it's going to give us enough information to show us how that structure is arranged, how those atoms are arranged. So C4H10 doesn't tell me an awful lot. I just know there's 4 carbons and 10 hydrogens, but it doesn't tell me how they're connected. So let's take another look back at our butane molecule. Here it is. How are those atoms arranged? So if we take a little bit at a time, just get rid of this C4H10. The first C has got 3 H's attached to it. Next to that, there is a C with 2 H's, and then there's a C with 2 H's, and then there's a C with 3 H's. This information is going to tell me all I need to know to draw out butane. and that would be called its structural formula. Let's just write CH3, CH2, CH2, CH3. Now you can simplify that a little bit and still get it right. Structural formula is the minimum you need to be able to draw the structure. So you could say that there are two CH2s repeating one after another, and then bookended by these two CH3s. CH3s are always at the end, never in the middle. Okay. So our next type of formula is called displayed, and this is where you have to show every atom and every bond. And so for butane, we started with its displayed formula. There were 4 C's in a row, and each one of those was attached to hydrogens, and we show out every single stick. So the sticks represent the covalent bonds between the atoms. And then the last, and probably the most frequently used type of formula, is called the skeletal formula, and that shows you how the carbon skeleton is arranged, the shape. So it doesn't show you the hydrogens, they get hidden. It's a simplification, it's a way that chemists can cut down what they need to write. So we start with 4 C's in butane. I'm going to put my pen down on the paper. I'm going to go C to C to C to C. This shows me how they are arranged, and what I've got here is, if I were to take a pen or a highlighter, we've got 1, 2, 3, 4 carbons arranged in a zigzag. We can't draw them in a straight line, they're not in a straight line anyway. If you look at the bond angles, they're 109.5 degrees apart, but I've got 4 connected in a line like that, and that is called the skeletal formula. So what we're going to do is we're going to practice those formulae types now with some other examples. So this is butane again, so we just did butane a few times there. So for this example we're going to take pentane, which has got 5 carbons, and it doesn't matter that you maybe didn't know that structure, but we're going to try to turn it into our different types of formula. So pause the video and see if you can come up with the molecular formula for pentane. And if you've counted that up, you should have seen that you've got 5 carbons and 12 hydrogens. And then if you look at that, you say to yourself, what would the empirical formula be? Is there a simplest whole number ratio of that? So 5 is a prime number, it's divisible by only 1 and 5, and 12 is not divisible by 5, and so the empirical formula is actually the same as the molecular formula. What about the structural formula? So you take each section as it comes, and you say, well, I've got a C with 3 H's, then I've got a C with 2, and then another C with 2, and counting my way down the chain, and then another C with 2, and ending on a C with 3. And how would that be in skeletal? So pen on the paper for carbon number 1, 2, 3, 4, 5. 5 carbons. So here's another one. I've drawn the skeletal formula this time, and see if you can turn that into the other types. It might be an idea to turn it into displayed first, and to do that you want to count the carbons. 1, 2, 3, 4, 5, 6. See if you can come up with each of these different types of formula. So there you go, I've come up, and you can see in the structural formula, because I'm repeating myself, CH2 4 times, one after another, I've just written that in brackets to save time. Let's have a go at another one. What if we were to give you the structural formula that looked like this? CH3, and then we're going to have a CH2, and then we're going to have a CH and a Br, and then we're going to have a CH3. So usually it's good to try to display it first, so try to turn it into a displayed formula. You take the first C and you put 3 H's on it. take the second C and you put 2. Then you take the next one and you put 1H and 1Br. It doesn't matter whether you go up or down, as long as you get 1H and 1Br. And then you take the last C and you put 3 H's. Now you want to look at that, you've got 4 C's. And count them up, you've got 9 H's and a Br. So there isn't anything simpler for that, so you just copy that down. And then for the skeletal, you would draw the carbon skeleton, 1, 2, 3, 4. And H's aren't shown, but other groups are, otherwise how would we know they were there? And so we have to put that Br on a stick coming off number 2. Just before we go, one last one. We've got our display formula there. Pause the video and see if you can think what that might look like for all the different types of formulae. And there you go. C3H6, which simplifies to CH2. The first carbon on the left has got 2 hydrogens, then we've got 1 in the middle and a CH3. And if we draw that skeletally, we've got 3 carbons, 1, 2, 3, and between the first and the second there's a double bond, so we draw a second line to show that double bond. These are the types of formulae we're going to be dealing with, and they're going to use these terms in organic chemistry.